This is part 2 of a review of integrating quotients. If you haven't seen part 1, either click the link that appears in the upper right hand corner or find the link in the description. For number 9, since we don't have polynomials in the numerator and denominator, we can't really talk about the degree of the numerator versus the degree of the denominator. We do have this hint that inverse trig will eventually be used. But other than that, you might have tried U-substitution and you would have just found that it didn't work out, at least not without involving inverse trig. So if I had to guess which one of the inverse trig rules I'm going to use, I see no square root, I see addition, so I'm betting it's going to be the arctangent rule. To use the arctangent rule, I need U squared. So I need to turn this e to the 6x into something squared. What could I put inside the parentheses that would make this term have the same value as e to the 6x? So let's see, how about e to the 3x? Yeah, if you raise a power to a power, you multiply. So if I wanted to get rid of the parentheses, I would multiply 2 times 3x, which would give me 6x. So these are the same. Now I have something squared. This tells me that my u is e to the 3x. That means my u prime, well, let's see, the derivative of e to the something is e to the something. However, there's always the chain rule. Because the exponent is not just an x, I need to multiply by the derivative of 3x, which is 3. But I choose to put that 3 in the front. So this is my u prime. Let's go ahead and do the substitution. So we have e to the 3x over u squared plus 5. Instead of dx, we will write du over u prime, which is 3e to the 3x. Aha! We have e to the 3x in the numerator and in the denominator. So these will cancel out and they are gone. On the next step, this 3 in the denominator will end up as a 1/3 out in the front. So now we have this. This integral is a perfect match for the arctangent rule, where a is equal to the square root of 5. A is always the square root of the constant. So let's go ahead and write the rule. So we have 1 over a, so that's going to be 1 over the square root of 5, and then arctangent u over a. So arctangent, and u is e to the 3x. So we have e to the 3x power over a, which is the square root of 5. And then we have the plus c. But don't forget the 1/3 that was out in the front. If I multiply 1/3 times 1 over radical 5, it'll just be 1 over 3 radical 5. This is the final answer for number 9. For number 10, we have this hint that inverse trig will not be used, but even without that hint, when we imagine trying to do U-substitution, because we have e to the 3x in the denominator and the numerator, we kind of can see that it will work out because something will cancel. Let's let u equal the entire denominator. So let's let u equal e to the 3x plus 5. In that case, u prime is going to equal, well, let's see, the derivative of e to the something is e to the something. However, the chain rule requires us to then multiply by the derivative of 3x. So I'm going to multiply by 3. This is my u prime. Let's go ahead and do that substitution. So we have e to the 3x over u. And then instead of dx, we will write du over u prime, which is 3e to the 3x. But just like we wanted, we have e to the 3x in the numerator and the denominator. So these will cancel each other out, which is great. This 3 in the denominator will wind up out in the front as a 1/3. So I now have 1/3 times the integral of 1 over u du. But this is a memorized rule. So I'm going to hang on to that 1/3. But the antiderivative of 1 over u is the natural log of the absolute value of u. So the absolute value of e to the 3x plus 5 plus c. So that's it for number 10. For number 11, you need to make sure that you have memorized this trig rule. For now, let's integrate term by term. Increasing this exponent by 1, we have x to the 3rd power. Then we divide by the new exponent, so that's 1/3. Moving on to the next term. And here comes the rule. I'm doing a mental U-substitution. So my u is 3x, which means my u prime is 3. So I will end up dividing by 3, which is why I am going to have a 1/3 in the front of this term. Now I move on with the rule. I have negative natural log cosecant u, absolute value of cosecant u plus cotangent u. So the negative I will put right here. And here's my natural log of the absolute value of cosecant u plus cotangent u plus c. And that's the final answer. Pretty easy if you remember the memorized rule. Number 12 is a trig problem. We have memorized the integrals of each of the 6 individual trig functions. Other than that, there are 4 other trig integrals that we have memorized. For example, we know that the integral of secant squared u du is tangent u plus c. That's because we know that the derivative of tangent is secant squared. And right along with that, we can talk about cosecant squared. So the integral of cosecant squared u du will equal negative cotangent u plus c. But we also know the integral of secant u tangent u du. This is going to be secant u plus c, because the derivative of secant is secant tangent. And right along with that, we know that the integral of cosecant u cotangent u du will equal negative cosecant u plus c. These are the only 4 trig integrals that we know, other than the integrals of the individual 6 trig functions. So when I see an integral involving a trig function, I often try to see if I can rearrange it to look like one of these. And one thing that I know is that if I take the cosine and move it up to the numerator, it will become secant. So if I move cosine squared up to the numerator, it will become secant squared. So I could rewrite this integral as the integral of, well, I think I'll just put x times secant squared of x squared dx. This would be the same thing. I know how to take the integral of secant squared u, so I can probably solve this by u substitution. Let's let u equal the x squared on the inside, which means that u prime is going to equal 2x. Performing the substitution, we have x times secant squared u. Instead of dx, we will write du over u prime. In other words, du over 2x. We notice that we have this x in the denominator and the numerator, so these cancel each other out. Yay! This 2 in the denominator will end up as a 1/2 out in the front. So now I have 1/2 times the integral of secant squared u du. So this is just like I thought. I know how to take the integral of secant squared u. It's just going to be tangent u plus c. Don't forget the 1/2 in the front, but now we have this. Substituting x squared back in for u gives us the final answer. Number 13. Find the exact area of the shaded region which is bounded by the x-axis, the y-axis, and the graph of f of x equals 8 minus 2 to the x power. Be sure to clearly write a definite integral that represents the shaded region's area before you start finding any antiderivatives. In order to set up a definite integral, we will need this intersection point right here so that we can write the limits of integration. So we need the x-intercept of f of x. We can find that by setting 8 minus 2 to the x power equal to 0. Adding 2 to the x power to both sides, we end up with 2 to the x power is equal to 8. 2 to the third power is equal to 8, so we know that x is equal to 3. So that is the x-coordinate of this intersection point. The area between f of x and the x-axis between 0 and 3 can be represented by the definite integral of f of x from 0 to 3. All we have to do is evaluate this integral. Let's take the antiderivative term by term. The antiderivative of 8 is 8x. And here comes a memorized rule. The antiderivative of 2 to the x is 2 to the x, but then you have to divide by the natural log of 2. And normally I would say plus c right now, but this is a definite integral, so it is time to apply the limits of integration from 0 to 3. This means we need to find the value at 3 minus the value at 0. So here is the value at 3 minus the value at 0. If this was a test, you should probably stop here and just put this as your final answer. Since we are just practicing, let's go ahead and simplify as far as we can. So now we have this. 8 times 3 is 24, 2 to the third power is 8. The 8 times 0 is gone. Notice that we had minus a negative, which became a positive, and 2 to the 0 power is 1. These last two terms are like terms. We have a negative 8 and a positive 1, and with the like denominators. So if we combine these into 1, we get the final answer of 24 minus 7 over natural log 2. Last one, number 14. Find the area of the shaded region which is bounded by the x-axis and the vertical line x equals pi, and the curve y equals tangent of x over 3. Be sure to clearly write a definite integral that represents the shaded region's area before you start finding any antiderivatives. So the area under the curve from 0 to pi can be represented by the definite integral from 0 to pi of the function on the top here. So that's going to be our tangent x over 3. So this integral does represent this area. Now all we have to do is evaluate. Let's start with the memorized rule. Actually, I hope that you memorized this rule. If you haven't, pause and memorize it right now. It helps me remember that tangent is sine over cosine. And that's why we have a cosine in this integral, because of the cosine in the denominator. Anyway, there's the rule. So I am going to use a mental U-substitution, because if my u is x over 3, or 1/3 x, then my u prime will be 1/3. When I do the substitution, all that's going to happen is I'm going to end up dividing by 1/3. And that's the same as multiplying by 3. So I'm going to have a 3 out in the front. Other than that, I can go ahead and apply this rule. So here it comes. Negative natural log of the absolute value of cosine u, which is x over 3. Instead of putting plus c, I am going to apply the limits of integration from 0 to pi. This tells me that I need to find the value at pi minus the value at 0. I think the calculations will be a little bit easier if we move the negative 3 outside of the parentheses. So I'm going to keep the negative 3 way out in the front as I do the value at pi minus the value at 0. So here's my negative 3 way out in the front. And here's the value at pi minus the value at 0. The cosine of pi over 3 is 1/2. So I'm going to have negative 3 times the natural log of 1/2 minus the natural log of, well, the cosine of 0, this is over here on the right-hand side of the unit circle, where the x value is 1. So I have the natural log of 1. And we know that the natural log of 1 is 0. So that term is gone. If this was a free response question, we would stop here and this would be the final answer. Negative 3 times the natural log of 1/2. The only problem is when we look at the answer choices, our answer doesn't match A, B, C, or D. One big clue is that none of these have a negative sign in the front. They're all positive. So let's take that clue and run with it. This was the most missed problem on the test, so I am going to explain it in a couple of different ways. The key is we have to use a property of logarithms, the power rule. If I have the natural log of a to the c power, the power rule says I can take this exponent and move it out into the front. So I could write this as c times the natural log of a. So how does that help me get rid of this negative? It's going to take me 2 steps by this first method. I'm going to rewrite this 1/2 as 2 to the negative 1 power. And as soon as I say that, you can probably see where I'm headed. So I have negative 3 times the natural log of 2 to the negative 1 power. But now I can use the power rule, take my exponent and put it to the front. If I take this negative 1 and multiply it out to the front, a negative times a negative is a positive, and I am left with positive 3 times the natural log of 2. So this is another version of the final answer, 3 natural log 2, and here it is right here. The answer is D. That is probably the most straightforward way to think about it, but I'm going to show you one more way. So this negative 3, this would be the same thing as having, let's say, negative 1 times 3 times the natural log of 1/2. Using that power rule, the other way. I can take this -1 that's in the front and I can put it up here as the exponent. So if I do that, on my next step, I'm going to have 3 times the natural log of, I'll put it in parentheses, 1/2 to the -1 power. See, I took the negative and I put it up here as the power. And hopefully you know that if you raise a fraction to a negative power, you're just going to do the reciprocal. So this would be the same thing as 3 times the natural log of 2. Kabam! Another way of getting the same answer.